A sample of nucleic acids of good quality must appear as a sharp band. Agarose gel electrophoresis for these biomolecules acts by separating them according to their molecular weight. This is the reason why a sharp band is characteristic of a single or very similar molecular size, limited to the resolution of the gel. Moreover, it can be said that in such conditions a sample is well preserved. And the band looks diffuse or dragged along the lane, a degradation phenomenon occurred. The sample of an initial molecular weight starts to lose some nucleotides at both ends and experiences some cuts at different points of the molecule. These events generate wide ranges of new molecular sizes, which, due to the resolution of the gel, are not distinguishable. The presence of other molecules can be noticed when running an electrophoresis. Proteins, for instance, are big and more diversely structured molecules. Nevertheless, these molecules are too big to fit the pores of agarose. Thus, a protein contamination is often seen as a signal at the top of the lane, as it appears in lanes 4, 5, and 6. Agarose concentration is related to the band pattern in the gel electrophoresis. A highly concentrated agarose gel will yield a very small pore through which big molecules will not be able to move, while small ones will. In contrast, a low agarose concentration will produce a big pore, causing small molecules to gather at the positive end of the lane, while big molecules are separated well. In this experiment, the bands move upwards as the agarose concentration increases due to the phenomenon controlled by the pore size. There are reported relations of agarose concentration and molecular weights. It is able to separate sharply for an adequate visualization of a range of sizes. These charts must be consulted to correctly choose and decide how to prepare a gel electrophoresis to the expected sizes of the fragments of interest. 3 agarose percentages were used. All the fragments in this experiment, but the RNA sample, range from 0.3 to 10 kilobases. The ideal agarose concentration to resolve them must be, therefore, 0.8 or 0.1%. Fast DNA ladder is well separated and sharp within this composition, being located at the central region of the lane. If a higher concentration was chosen, as in the case of 2.5% agarose, the molecules of higher molecular weight in the ladder start to gather at the top of the lane and are not quite sharp, despite they have very different sizes. To observe the state of markers after the run is very important. Fast DNA ladder shows horizontal bands, which is desirable, but they are barely seen. This issue can't be caused due to a low sample quantity. After referring to the manufacturer's specifications, it becomes clear that fast DNA ladder is much less concentrated than the other 2 markers. The concentrations of fast DNA ladder and 2-log are respectively 25 micrograms per milliliter and 1000 micrograms per milliliter. In fact, the manufacturer of 2-log suggests a dilution in sample buffer to resolve the marker. 100 base pairs markers show a similar bandwidth to 2-log, so their stock concentrations must be similar. When loading a large sample amount with high molecular weight DNA, curved bands may result due to an uneven distribution of voltage. This problem may also be addressed by checking the buffer was prepared properly. To choose the correct buffer, it is necessary to define whether the sample is going to be recovered after the run, to estimate the size of the fragment of interest, and to know the type of molecule to be separated. For instance, if it is a single-stranded or double-stranded DNA. Some buffers are more suitable for some type of molecule, some voltage level, and run duration. As for the agarose concentration, charts are available, in which the advantages of each buffer offers are highlighted in different aspects. TAE buffer is suggested for low agarose concentrations and short runs. In fact, TAE buffer resolves bands better in both figures of equal agarose concentrations.
Another type of buffer is also used in electrophoresis, the loading buffer, which helps to visualize and render the samples denser in the well. For it uses different type of dyes and another compound for sedimentation of the samples. Each dye has different migration pattern, and that is the reason why the loading buffer composition depends on the size of the samples that will be separated. The most common dyes are bromophenol blue, red cresol, orangey, and hyalinsinol. Due to the size of the samples, in this experiment the most suitable dyes were hyalinsinol and bromophenol blue, which were used in a concentration of 0.25%, and glycerol was used for sedimentation in a concentration of 13%. Fecal can also be used for give density to the samples. In order to visualize the nucleic acid in the agarose gel, the samples are stained with dyes, which are interspersed in the bases of the DNA, and when the dye binds DNA, is more fluorescent than the dye in solution. In this experiment, gel red was used for stain, and the main advantage of gel red against ethidium bromide is that it doesn't have mutagenic activity and there is no risk of environmental contamination. Staining can be made after electrophoresis or dye is incorporated into the agarose solution. The results obtained from post-staining with the gel red have superior sensitivity and eliminates the possibility of dye interference with DNA migration. In this practice, staining was made with the gel red in a concentration of 1x, which was during gel preparation. This could mean that the migration of the samples could be affected by the staining. Finally, another variable that could affect the results is the voltage applied during electrophoresis, because it can affect the integrity of the gel of the samples. The running in this experiment was performed at 100 volts for 16 minutes. As a general rule, higher voltage, higher displacement speed. When voltage is too high, the resolution decreases due to the overheating of the gel. When voltage is very low, the migration of the band is reduced and the bands widen due to diffusion. It can be seen that the gels have low resolution, especially with the gels with TBE buffer, so it can be assumed that the voltage was not adequate and it was a very voltage. In order to select the appropriate voltage, the size of the DNA to be separated is important. Larger size, lower voltage is required. According to above, for samples such as the PCR product of 450 base pairs, the voltage was adequate, but in case of samples such as E. coli genomic DNA, a lower voltage was necessary because the size is greater.
The molecular weight markers present distortions due to the excess of sample added to them. So the calculations and dissolutions must be adjusted for their load. The PCR products showed to be specific and very abundant, whereas the sample of genomic DNA and PCR topo present degradation. In addition to having contamination by proteins in the case of the plasmid, the conditions of displacement are adequate, reducing the amount of sample, taking into account that the TAE buffer is the most recommended by the general characteristics of the samples.